Hello, and welcome to the series where I take a game I started in high school and try to improve it using knowledge that I've gained along the way. In the last video, I used off-screen buffers to try to smooth out the animation, but as a result, things got very slow. So today we're going to look at how I can speed up drawing using stack blasting. Before we start, a big thanks to Glenn's blog at nowhereman999.wordpress.com. He has a great series on speeding up your code, including a nice introduction to stack blasting. A lot of my starter code came directly from his blog, including this series and other places, so I highly recommend it if you want to read more. Another great read is this article by Tom Moertel. He came up with stack blasting on his own back in the day for the 6809. And this is a neat walk down memory lane about how he came up with it and the issues he ran into. Highly recommend it if you're curious to read more. So recall from the previous video that what I'm doing differently now is I redraw each frame from scratch. And part of that involves redrawing the static portions of the screen. So at the top I have this kind of yellow area, which is where I would be showing the scoring. Underneath that I have this blue sky, which is generally unchanged. And then down here I have this whole large green area that the car sits on top of that also does not change. These checkerboard areas are the parts that do change. These would be the mountains that scroll by. This would be the ground that scrolls by. So I'm going to focus on the code that draws these static portions of the screen. They basically fill a register with a static value, like the bytes for yellow or the bytes for blue, and it copies them to the parts of the screen buffer where they need to go. This code here is an example of a fairly standard loop. It copies 2 bytes at a time, so I preload my X register with these bytes, which are yellow. I preload my U register to point at the graphics area, and then I just copy those 2 bytes, advance U, and then I decrement my loop pointer, rather variable, which I initialized up here, and then I just loop back up. So this is kind of the typical way you do it if you weren't really thinking about making things as fast as possible. But how much does this really cost? LWASM can generate for you cycle counts for each line, and inside this loop the line that really matters the most is this one here. That's where I'm copying the bytes. So each time I copy 2 bytes I'm using 8 cycles. And I say these don't matter as much, but actually that's not really true. I mean, I am doing this every time through the loop. I'm doing this every time through the loop. So you can actually say for 2 bytes I'm spending 8, 10, 13 cycles. So the first thing one would do is to try to unroll this loop. So rather than having a loop at all, I could just load a register to point to the static bytes that I want to copy. I could point this time X to my graphics area, and then I just store that wherever X is pointing. Each time I advance X a little further along. So I don't have any conditional branches, I don't have any loop variable. So how much does this cost me? It only costs me those 8 cycles per byte pair. So each time I do this, I'm spending 8, 8, 8, 8, and that's it. So that's a total of 32 cycles. Now you could argue and say, well, as convenient as that ++ is, you are paying a penalty for that. We could get rid of this and use offsets instead. So in this example, rather than advancing X, I just change my offset. So I'll store my D wherever X is pointing, leave X alone, but then I'll store my D 2 bytes offset, and then 4 bytes offset, and then 6 bytes offset. So are we gonna save much by doing this? Well, rather than 8 cycles each time, now it's 5 cycles for the first one, and 6 for the other ones where we actually have an offset. So now we're up to a total of 23, whereas before we had 32 cycles. So that actually does save a whole bunch. But can we save more? We've been using the store D instruction to store D to write to memory. Is there any other way to write to memory? If you look through all the opcodes there are, would you find some other way that you could write? Well, you might just skip over the push instruction because, well, that's not really writing to memory arbitrarily. That's really just for use with the stack. But the stack is really just a register that points to some address, and push is just a structured way of writing the values of registers wherever S is pointing. So what if I write 8 bytes to memory with a single push instruction? There's some stuff I need to do to get things ready, but how much would this cost to get those 8 bytes written into memory? Well, what took us 23 cycles before is now only 13. It only takes 13 cycles to write 8 bytes. Now you could say that I'm cheating, because there was that stuff we had to do up front. Most notably, we had to populate all of these registers with that value, that 55 hex value to begin with. How expensive is this? This is actually another 13 cycles. So in all honesty, I am spending 13 up front and another 13 here. But it's not that bad because I actually wasn't really counting what it took to prepare the previous ones. I wasn't counting these cycles either. But yes, they are less. They are fewer. So we are spending more time up front, but this you do once. And this, presumably, you're going to be copying more than just 8 bytes. So you could repeat this push over and over and over again, and then the overhead that you spent up front diminishes. So here's what I came up with for my game. So first, I have some blocks of code to prepare to do the stack blasting. So this will initialize variables to do that yellow status bar at the top. This will initialize variables to do the blue sky at the top. And then finally, this will initialize variables to do that green background near the car. Each time they're calling this subroutine fill static rect2, and this is the thing that's doing the stack blasting. The first half only executes once each time. This is not in a loop. This just initializes the stack pointer to point where the color pattern lives in memory, uses that to populate my registers with that pattern, and then repoints S at the end of the screen memory. The blasting happens here. We push, check to see if we're done, and then branch up. Push, check to see if we're done, then we branch up. I call this baby stack blasting because this is like the simplest possible case you could imagine. We're just blasting static bytes. Things get more hairy when you're trying to copy sprites or backgrounds or patterns from a buffer in memory into the screen buffer, and we will be talking about that later. But for now, let's just focus on what you've got to do just to do the simplest bare bones stack blasting. And that's the stuff that I keep glossing over. We have to remember that the stack pointer is actually supposed to be used as a stack. So whatever it was, we're going to temporarily store it. We're going to preserve it in this location in memory so that I can restore it at the end. The other hairy thing is the order in which things get pulled and pushed. The pull instruction assumes the stack is pointing right at the very last thing that was pushed, and it advances the stack pointer to larger addresses each time. So it assumes that it's pointing to the first byte of this register, and then it starts reading into larger and larger and larger memory addresses until it reads all of these values. So you can think of pull as going in the normal order, from small addresses to large addresses. So if I keep my patterns here, this is my yellow, this is my blue, this is my green, you'll see these are each 8 bytes long because that's how many bytes we blast at a time. We can start the stack pointer right here at the beginning, and it will happily read these in order. But when it comes time to write those bytes, that's when we use a push, and push goes the opposite direction. Push starts at a larger address, and then S goes to smaller addresses as it writes these bytes into memory. So I need to position S at the end, and that's what this is all about here. I'm keeping track of where the end of the area of the screen buffer is that I want to write to, and then S will go to smaller and smaller and smaller addresses as it does the pushes. Then my loop condition checks to see if I've reached the beginning of the area of the screen buffer where those colors need to be. You can visualize the stack like this. So imagine this is my buffer in memory where I store the pattern that I'm going to want to blast. You start by positioning S to point at the very first byte. And so each time you pull, S will take that value, stick it in a register, and then move S to the next address. Pull, 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 pull. And then after it's done all of the pulling that it needs to do, those registers have been populated. At that point, you reposition S to point to the just past the end of the screen buffer that you want to start writing to. So imagine this is not where we want to write. We want to write up here. We intentionally position S 1 byte forward, and then with the next push, we decrement S and we write that byte. We decrement S with the next push, and we write that byte. Push, push, and that's how those bytes get written into the screen buffer. So as an example, imagine that we're writing this blue region into the screen buffer. S needs to start here. Actually, it needs to start at the very beginning of the line right after the blue. And then the very first push is first going to decrement the stack pointer to here and start writing the bytes. And each push is going to move it further and further toward the beginning of memory, right to left, and then up again, right to left, through each line, until it finally hits here, the start of the rectangle. And so the loop boundary condition asks if we've reached the start of the rectangle, then we're done. And one final gotcha to be aware of. I'm going to illustrate what happens when we run this. It's actually really cool. But first, let's just take a quick look at what the code is doing. So as you saw before, I am just loading my stack pointer to point to that region of memory that stores all the 5555s. It'll store 8 bytes of those. And then it reads those into the registers. It positions S to be at the end of the screen buffer. And then we, in a loop, push them, push them, push them, push them. We started at the end, and we keep on going so long as our stack pointer is about 10 lines or fewer from the bottom. So once we reach 10 lines up, that's when this loop stops. But then, this was all a big outer loop, so we're just going to go back up here and start over again. So what you're going to expect to see is an uninitialized screen buffer except for 10 lines of yellow. And it's just going to keep rewriting those 10 lines over and over and over again. Now looking at this, you wouldn't think anything bad or terrible would happen. This should be fine. It'll just be boring to watch. But it is not boring. Let's take a look. Now I'm going to pause it right here just so we can take a look. This is what we expected. So the checkerboard pattern, that's the uninitialized screen buffer. You see that the 10 lines of yellow, that thin stripe at the bottom. And so what we would expect is it'll just keep redrawing that yellow stripe, but we won't notice. It should just look like this screen will stay like this. But I'm going to let it go and let's see what happens. So, oh, there it goes. All of that yellow disappeared, and you can kind of see this little shimmering that like keeps on happening. So what's going on? Like, it's still running, it still seems to be redrawing, but the stuff it's redrawing is no longer all that yellow junk. Instead, it's this other weird junk. To the debugger! Let's use the debugger to see if something happens to this region of memory that stores our yellows, because after a while, after we started redrawing, it wasn't really redrawing those 55s anymore. So that starts at 3F85. So we're going to load up our code. And we can set a watch point at 3F85 for 8 bytes as a write. And it will alert us if something happens. And boom! Something definitely happened. So first, let's take a look at where we're at. 010C. You saw the code, folks. How could we end up here? What even is this? 010C, that's the interrupt vector. And if we look closer, the debugger is telling us that the program counter at the time that the watch point was triggered was 3F0B. And 3F0B is that pull instruction. So this is where we're reading the yellow. So when we were reading the yellow, an interrupt got triggered. I'll be talking a lot more about interrupts in future videos, but the quick summary is that when an IRQ gets triggered, the 6809 needs to save the registers. And where does it do it? Where does it save anything? The stack. So right while I was trying to read from my repositioned stack, the 6809 was saving the full state of everything to my redirected stack pointer. In fact, if we take a look, we see some of those 55s, but then we see some other stuff. 3F0D. What's 3F0D? 3F0D is the very next instruction. So this was what it looks like when the 6809 stores what the return address needs to be from the interrupt. When the interrupt is done, it needs to know to resume execution at the very next line. That's 3F0D. So those patterns that you saw were yellows mixed with that 3F0D. And if we have this run some more, now you can see those 3F0Ds really started filling stuff up there. And pretty much all my yellows are gone. 3F0D, 3F0D, 3F0D. But that doesn't explain everything. There's still this weird shimmering. I'm going to actually disable the watch point. And you can see we have this weird, like at various points, a very strange, very quick shimmering. That's because the interrupt can happen at any time. My watch point is only catching when the interrupt happens when my stack pointer points at that yellow region. But what if the interrupt happened while I was in the middle of blasting? If it happened here, then my stack pointer was no longer pointing at the yellow buffer. It was pointing at the screen buffer. So at any point in here, if we had an interrupt, it would start writing the state to the screen. And that's what you're seeing here. Every time the interrupt happened, it would use the screen to write the state of everything. And then quickly that would be undone as we returned to the code, and the code ended up writing what it was trying to write from the yellow buffer. So the moral of the story is, before you start doing stack blasting and using the S register for your own purposes, maybe you want to disable the interrupts first. And I'll be talking more about this code in a future video, but this very quickly just disables the vsync. So let's see how fast the scrolling works now that the static regions are being stack blasted. That is still kind of slow. How does this compare to before? And how does this compare to the original before I started doing off-screen buffers? So it looks like adding the stack blasting did speed things up a little bit, but we're not at that speed that I was at before I started doing the off-screen buffer. My next task is going to be to do stack blasting for the moving portions of the screen. So I need to be stack blasting the mountains, and I need to be stack blasting the ground. And it's done. Let's take a look. Looks like I have a bug to deal with. And it's fixed. Let's take a look. Okay. Alright, third time's the charm, folks. Here we go. Jeez. I think I might need to rename this from Moon Patrol to Warped Reality Patrol. Then the graphics will match the name. Alright, I'm sure I've got it this time. Whew, there we go. That looks not only correct, but also faster. So in the next video, I'm going to talk about all of the madness that went into making this work. And folks, it is crazy.